Good day, and welcome back to Trig Equations. Today we're going to be looking at modified periods. So in a case like this, where we have sine of 2 theta equals 0.5, it's a little different from saying just sine of regular theta equals 0.5. From a transformation standpoint, or considering function transformations, it's like we've modified that period by changing this b value right here. Now there's a 2 instead of a 1z. Solving this is very similar to solving this one. As with any function to solve, we want to isolate the argument itself, everything inside those brackets, and then we can solve for the variable from there. So hereabouts, we want to isolate what's in these brackets. So we'll isolate 2 theta, and then once that's isolated, then we can finish off by dividing by the 2 and isolating the theta. There is one other little bit of a trick. Now suppose we're solving this on a particular domain. So we're solving this equation. Sine of 2 theta is 0.5, but theta goes from 0 to 2 pi. When we isolate this argument and we find all of its coterminal angles that are within the domain, we do have to note that if theta goes from 0 to 2 pi, then 2 theta will go from 0 to 4 pi. How do we get that? Multiply this by 2, multiply this by 2, multiply this by 2. And that is the new domain. We're going to work on this particular example all the way through. So let's solve sine 2 theta equals 0.5 over this given domain. Woo! So we are told, once again, I'm just going to start with the equation, that sine of 2 theta is equal to 0.5. And we know that since theta goes from 0 to 2 pi, we could say that 2 of theta will be somewhere between 0 and 4 pi. When we are solving something like this, if I were considering, say, sine x is equal to 0.5, I would get a reference angle, and I could say that the reference angle would be pi over 6, or 30 degrees in this case. But we're not isolating x, we're isolating 2 theta. So instead of saying something like sine of x, instead of saying something like the reference x is equal to pi over 6, we're actually going to say that that's a reference for 2 theta. That's that very, very slight, subtle difference there. So it's not theta sub r, it's 2 theta sub r, because that was our argument within those brackets. If we were just dealing with 0 to 2 pi, then we could say that this angle could be pi over 6, or it could be where we sine is positive, so 5 pi over 6. And that's same as taking this reference angle and saying, well then, x could be pi over 6, or x could be 5 pi over 6. So just continue with the scrap work on the side here. So note that parallel. So this is exact same as this. This line is same as this line. Just instead of x's, we have 2 thetas. Now again, this little bit of solutions will take us from 0 to 2 pi. And that's all good and well for theta, but 2 theta, again, could go from 0 to 4 pi. So we've got more solutions. So if we're going to add one revolution to each of those, 12 pi over 6 plus pi over 6. So coterminal angle, we've got 13 pi over 6 and 17 pi over 6. So these are our solutions from 2 pi to 4 pi. Again, because 2 theta can be in a much larger span. At this point, we have solved for 2 theta. All that's left is to solve for theta itself. So if 2 theta is pi over 6, theta would be pi over 12, just dividing both sides by 2. Or in this case, 5 pi over 6 divided by 2 is now 5 pi over 12. 13 pi over 6 divided by 2 is 13 pi over 12. And 17 pi over 6 divided by 2 is that. So we've got all those options. If you want a nice formal concluding statement, that would be handy. And we can say that theta has to be something from that collection. And it's done. Woo! That was fun. There are 2 more examples to go through, so not very many. One is non-calculator, one is with a calculator. I'll be explaining all the steps I do as I go through them, so if you feel like you have a handle on it, then you can kind of speed through those sections. And if you still want the full-on description as I go along, then just play it along. But I do encourage you to actually give these a try. So looking at this equation, give it a try on your own first, see what you can do. If you want, on scrap paper, you can try solving a slightly different equation. So you could let 3x be represented by some other variable. U? Sure, why not? So then on your scrap paper, you can solve cos squared of u plus 3 cos of u plus 2 equals 0. And solving that will give you a bit of a basis for solving this equation. That is, again, if you want to use scrap paper. Again, give this a try, see what you can do, see what answers you come up with, and then compare them to what we get here. I'm looking at this. We're told it's non-calculator. It must be in a non-calculator section of the provincial. So I'm going to assume this is probably factorable. And in fact it is. We're going to have cos of 3x in both of these brackets. And just straight up a plus 2 and a plus 1 equals 0. And then we can start isolating things. So those are our 2 options. Note, of course, this option is not possible. Cos of anything can't be -2. We know that cos of anything has to be between -1 and 1. So this is a big no. This one has no solution. But this one we can work with. Now again, if this just said something like cos of u is -1, we could get the reference u. Cosine's graph looks like this. This -1 happens at pi. So that's what we'd be saying. The reference angle is pi. So similarly, the reference version of 3x, that's an r, is equal to pi. Hooray! We do have to finish this off a little bit. And when we do, let's consider the domain. X can go from 0 to pi. And if that's the case, then 3x will have 3 times the span and go from 0 to 3 pi. So when we look at our options here, well, from 0 to 2 pi, we have that. So this is our answer from 0 to 2 pi, that first revolution. But we can go as high as 3 pi. So there's another revolution in there. If we add 2 pi to this, get something coterminal, we get 3 pi. You could say it's from 0 to 4 pi as well, but note that our domain does cut off at 3 pi. So we're not actually going 2 whole revolutions. This just happens to fit in that other revolution. That is the biggest key step. That is complete. Now we can solve for x just by isolating it's being affected by this 3. So x is pi over 3. Or x is pi. You are welcome to leave your answer like that. That is considered acceptable. But moi, I just want an excuse to draw curly braces. So there are my answers. Whew. What fun. Lastest example. Ciao. I didn't actually scroll. Oh, this thing freezes sometimes. All right. Last one. Again, give it a try. This is a calculator example. Who knows what we'll need the calculator for? But we'll try it. We'll see what happens. Again, give it a try. Note our domain is from 0 to 1080 degrees. And so we'll see how that affects our answer. And once again, if you feel like you have more of a handle on things, you can speed through this. But please do give it a try before just continuing. So try this example, see what you can do, see how far you get, and see where that goes. If you want to try something on Scrap, maybe let's just stick with u. That's a good parameterizing variable. Let u equal half x, and then you're solving that instead, which is a bit nicer than seeing the half x there. Ooh, scare us stuff. Okie day. I'm going to go ahead with this. I'm going to factor it. So something will go there. Oops. And something will go there. This also has to give me a 3 and a 1. And looks like a plus there and a minus there. So we're good. Okay. 2 possibilities from this. If you want to write down the sub-step here and say that 3 sine of half x minus 1 equals 0, you are welcome to do that. You can even then say that 3 sine of half x is equal to 1. You don't absolutely have to put those. What is key is that you can note that sine of half x is 1/3. And similarly, you don't have to write down that sine of half x plus 3 equals 0. You do not have to Oh wait, yeah, you don't have to write down that one line. You do have to state at some point that sine of half x is negative 3. So those are our two options there. Checking this first one out, we need a reference angle. And once again, that's kind of like considering what if we said sine of u was equal to 1/3. We'd have to get some reference angle there. That would require use of a calculator. And from 0 to 90 degrees, we're talking about a value of 19.471 degrees. Thus, for us here, our reference angle is 19.471 degrees. But we're not talking about a u being there. We didn't use a u. We used half x. So half x, but it's our reference version of half x. So this stuff is just scrap. It's gone. Let's take a look at that domain before we go further. X goes from 0 degrees to 1080 degrees. So half of x will cover half of that span. Half of 0 is 0, half of 1080 is 540. Oakley dokley. So let's close off that bracket. Blink. So we can go more than one revolution is what's key here. We're not just going to go from 0 to 360. We'll go a bit further. So there's my reference angle. We are dealing with sine. Sine is positive, quadrants 1 and 2. So in quadrant 1, I don't need those brackets, what am I doing? We've got 19.471 degrees. And in quadrant 2, 180 minus that is 160.529 degrees. And those would be our answers from 0 degrees to 360 degrees. But we can go further than that. We can go as high as 540. So what happens when we add 360 degrees to each of these? Uh, 19.471 plus 360 gives me 379.471. And 160.529 plus 360 is 520.529. Oh, don't forget my degree symbols. That was close. So those are the ones that take us from 360 degrees to 540. Those are all of our possible values for half of x. We just need to finish off by saying what x itself is. So for this first case, x could be, what am I doing? I'm multiplying that by 2. So 38.942. Or x could be that times 2. Or this. Or this last one. There is one thing I did that I probably should have done differently, just with regards to rounding. And I'll mention that in a bit. Let's just finish off this answer here. again, it's valid to leave it like that. But why not use curly braces when you can, you know? So it could be this first angle, or it could be this second angle. Or notability you could sketch out right there. Okay, great. Or this third angle. Or this fourth angle. Interesting stuff. I mentioned I might have made a rounding oopsie that I should have done a little differently. All these answers actually did work out well in this case. In this case, I wouldn't get a rounding error for this particular problem. But I would recommend in this step, or even when you get the reference angle right here, add a couple extra decimals, a little bit more than you need. I don't remember exactly what it was. It was like 4712, and I don't know what was after that. Reason being, when we multiply by 2 to get here, if this was like a 4716, no, that wouldn't be a 6. If this was a 4714, then when we multiplied by 2, this last digit would actually round to a 3, not a 2. So I would have gotten a rounding error there. So just watch out for that. I would recommend, because this is not a final step. Our final step needs to be rounded accurate to 3 decimal places. So make sure before that you're keeping things a little bit more precise. So I'd recommend like 2 extra digits just to be super safe. And that's about that. If you do have questions, comments, concerns, because this is our first really new concept tackled this unit, then please don't hesitate to voice them. Let me know what you're thinking, what you're feeling, or if you're not sure what happened in these examples, I could find other ways to go over them with you, or perhaps produce new ones. But you just let me know what you need, message me over Teams, and that'll be pretty wicked cool. There is some practice work for you to give a try. So try these questions, see what happens, see how they go, and with answers below, you can of course, again, just let me know if you encounter difficulty and how I can best help you. That's it, that's all. I hope you've enjoyed how many times this video I went into a monotonous voice, except for the excitement of practice and answers. Yeah, bye.